Hello, AP Statistics students, and welcome to the College Board virtual instruction for AP Statistics. My name is Luke Wilcox. I am an AP Stats teacher at East Kentwood High School in Kentwood, Michigan. And today is Wednesday, April 15th. And we are going to waste no time today and jump right in. So let's see what we have up for today's lesson. First of all, let's check to make sure we are in the right place. You should be looking for AP Statistics, I hope. I have already introduced myself. My name is Luke Wilcox, East Kentwood High School. I do have some quick reminders here. If you've been with us for the last couple of weeks, you probably know this already, but if we have anybody that's new with us today, we are meeting on a daily basis, Monday through Friday, 2 o'clock Eastern Standard Time every day. You will either see myself or my esteemed colleague, Mr. Brandon Murphy. We're sort of working on a mostly every other day schedule. Currently, we are right in the middle of our AP exam review. We are the week of April 13th. This week, next week, and the week following, we will be reviewing stuff from the very beginning of the course, units 1 through 5. And of course, this is all in preparation for the AP exam, which we now know is going to be on May 22nd. So if there are any resources that you need for these lessons, which is the actual lessons themselves, as well as the homework problems that we are assigning, you can download those as PDFs at statsmedic.com/YouTube. You'll just look for today's date, April 15th, and you will see the resources that go along with today's video. Final reminder here, if you are a student or you know another student who will be taking this AP exam on May 22nd, which is an at-home exam and requires a device as well as internet access. If that is a problem for you or for someone else that you know, please give them this website address, cb.org/tech, so that they can make a request to get a device or to get internet access so that they can take that AP exam. I do know that the College Board is deeply committed to making sure that every student has access to taking that AP exam on May 22nd. So please utilize that if you need to. All right, so I'm gonna go back to the homework problem that you got from Mr. Murphy yesterday, which is gonna be a bit of a preview of what we're gonna talk about today in terms of analyzing two variable data. So hopefully you got a chance to try it, but let's go ahead and see how we did here. So here's what it says. A wildlife biologist is interested in the relationship between the number of chirps per minute for crickets, Y, and temperature. Based on the collected data, the least squares regression line is Y hat equals 10.53 plus 3.41x. I'm going to pause real quick right there and remind you of some general notation, which we're going to be seeing a lot of today. Anytime you have a line of best fit, typically we're going to call that A plus BX. And the important things to remember is that the B value is the slope and the A value is the Y-intercept. Now, I think it's also important to note right now what the variables X and Y represent in this context. And so they've told us already that this Y variable represents the number of chirps for the cricket, and the X variable is the number of degrees Fahrenheit by which the temperature exceeds 50 degrees. So this is a certain measure of temperature. So we're going to have to know that X is temperature, which is the explanatory variable, and Y is chirps, which is our response variable. Now let's get down to the question here. All right, it says, which of the following best describes the meaning of the slope of the least squares regression line? Well, first things first, we need to know what the slope is. And we know that that is the B value, or the value that is attached to the X. So 3.41 is our slope value. So right away, if I look at the answer choices, I can actually get rid of a couple of those choices. Answer choice A is making some sort of interpretation of 10.53, which we know is the Y-intercept. And I'm seeing the same thing here on answer choice C. So I'm going to get rid of that. Now, answer choice B and answer choice D have that 3.41 that I want. But let's look at answer choice E here. It says the slope has no meaning because the units of measure for X and Y are not the same. Well, when it comes to slope, you do not have to have the same units for X as you do for Y. This is certainly not the answer that we're looking for. So we either know it's answer choice B or answer choice D. Now, the way that we're going to arrive at the correct choice here is to go way back to your algebra days when you first learned slope, and my guess is at some point one of your algebra teachers called it rise over the run. And maybe even better than that, the change in y over the change in x. But if we put that in the context of this particular problem, when I say change in y, that's the change in the number of chirps. And if we want to get technical here, it's not just the number of chirps, it's actually the predicted number of chirps. That's why we include that hat on top of the y. And then on the bottom, the change in x is really going to be the change in temperature. Now, we know what the slope is. We know the slope is equal to 3.41. But I'm going to write that as a fraction of 3.41 over 1. And here's the reason why. When it comes to interpreting slope, we see it right here. It's saying if we had a change in temperature of 1, an increase of 1 degree in the temperature, we would expect or predict the number of chirps to go up by 3.41. So which of the two answer choices says that? Well, I think it's right here, answer choice B. For each increase in a temperature of 1 degree Fahrenheit, the estimated number of chirps increases by 3.41, which is exactly what this is saying right here. And if you look at answer choice D, for each increase of 1 chirp per minute, there's an estimated increase of temperature of 3.41. They've actually switched the X and the Y. That's why this one here is incorrect. So we definitely say that answer choice B was the correct answer here. So I hope that you did all right on this one. All right, let's go ahead and jump into today's lesson. The way that I always start these lessons is by giving you a quick overview of the learning targets for this particular lesson. And there are 3 of them. And we've got a lot of ground to cover here in today's lesson. All right, so let's take a look. Learning target number 1 is to describe the relationship between 2 quantitative variables. Okay, last time I was with you on Monday, we talked about describing 1 variable data. Today, we're going to talk about the relationship between 2 variable data. Next up, calculate and interpret residuals as well as residual plots. So we'll definitely look at an example of that. And then the last one is sort of a catch-all. There are a ton of interpretations that you just have to know in this particular lesson. Namely, you have to be able to interpret the slope, the Y-intercept, standard deviation of the residuals, and the coefficient of determination. So we're going to go through each one of those, being very specific about what the language should look like when you are interpreting those values. So let's go ahead and take a look at today's activity. And specifically, let's start with the context here, which may be one that's fairly familiar to you, and that's the SAT score. And what we're trying to do here is to predict an SAT score from a student's GPA. Most definitely, I would think that there would be some sort of a relationship between a student's GPA and how well they do on the SAT. Not an exact relationship, but at least some sort of a connection between those two. That's what we're going to investigate. So here's what the context of the problem says. It says, how well can we predict SAT scores from students' grade point average, GPA? Let's start by looking at data from a random sample of 10 seniors from a high school in Michigan. So we actually have the data here, first of all, represented as a scatter plot, which is the most common way of displaying 2 variable data. So let's look at each one of the variables. The first variable is GPA. The second variable is SAT score. And the first thing we want to recognize here is that each one of those variables is a quantitative rather than a categorical variable. So we will only use a scatter plot when we're trying to represent the relationship between 2 quantitative variables. Now, the other thing that we might want to know is which one of the variables is explanatory and which one is the response. Well, the explanatory variable is the one that's going to help you make the prediction for the other variable. In this case, we think if we know a student's GPA, it should help us predict their SAT score. So we would say that the GPA is the explanatory variable. So the other variable, the one that we are trying to predict here, is the SAT score. That is what's called the response variable. And we are always going to put our explanatory variable on the x-axis and our response variable on the y-axis. Now, we also have some computer output here, and it is super critical that you're able to interpret computer output quickly. You know what the values represent. So let's just do a quick high-level overview. if you're trying to find the equation for a line of best fit. I know I showed you in the homework problem that this is the typical form that we use, right? Y hat equals A plus BX. Now that A value is the first number that's given to you in the computer output, and the B value is the value that's right below it. And that's going to give us the numbers that we need in order to write the equation for the line of best fit. Now I'm just going to give you that quick reminder again that the A value is the Y-intercept and the B value is the slope. Now we're going to talk about some of these other values in this computer output as we work through the activity for today. All right, so let's get into the questions here. Question number 1, is this a positive or a negative relationship? Well, I think very clearly by looking at the scatter plot, you see that upward trend as we move to the right, which is in fact indicating to us that we have a positive relationship. But we also want to be able to explain that. And what it means to have a positive relationship is that as the GPA goes up, we are noticing that the SAT scores tend to go up. We're moving in this direction, right? So let's put that into words. What we're going to say here is that students with higher GPAs tend to have higher SAT scores. And actually, we could say it in the other direction as well, right? Students with lower GPAs tend to have lower SAT scores, right? That's explaining why we have a positive relationship here. All right, let's move on to question number 2. It says, are there any unusual features of the scatter plot? So now we're just looking at the dots that are in the scatter plot there and trying to see if any of them look like they're sort of out of place. And of any of the values that I see there, I am a little bit worried about this value right here. That would be the student that had a GPA of about maybe 3.4. That seems to be pretty far away from that line of best fit. And so I'm going to go ahead and call that an outlier. Sort of similar to what we did with one variable analysis, except we don't have a fancy rule for deciding outliers. So you sort of have to just eyeball. Does it fit the trend of the data? Does it not? How far away from the line of best fit is it? But I'm going to call that an outlier. So I'm going to say that the student with a 3.4 GPA is an outlier. Now, in terms of this idea of unusual features, there's really a couple of vocabulary terms that you have to know, things that you could be looking for. The first of which is the one that I've already mentioned, which is an outlier. So let's get a little bit more formal with this, all right? The definition for an outlier, first of all, is that it doesn't follow the trend. Right? It doesn't follow the general trend of the rest of the data. But here's the other part that's really important. It has a large residual. And what I mean by residual is the difference between where that value is and how far vertically it is away from the line of best fit. In this case right here, this is the residual. And we do have a fairly large residual for that value. So that's why I went ahead and called that one an outlier. Now, one of the other vocabulary terms that you need is to be able to identify a point that is known as a high leverage point. Now, here's the deal with high leverage. It has to be way up here in terms of the X values or way down here in terms of the X values. So it's like way far out on either the low or high end of the X values. So I'm going to say that it has very large or very small X value. So you're looking for a dot that's sort of far away from the rest of the dots in the positive X direction or the negative X direction. And we don't tend to have that here in the picture. Most of the dots are sort of fairly clumped together. We don't have one that's way far off on the right or way far on the left. So I wouldn't indicate here that we have any high leverage points. Now there's one other vocabulary term that you might need here, and that's to be able to identify a point as an influential point. And the definition for influential point says that if you were to remove that point, it would have a substantial effect. So there would be substantial changes to a couple of things. It could have a big change on the Y-intercept A. It could have a big change on the slope B, and or the correlation value R. So if it had a big impact on one of those by removing that one point, we would say that that point is influential. And oftentimes an outlier or a high leverage point is also considered an influential point. So let's move on to question number 3, which says, what is the form of the relationship? Now for AP statistics, in terms of the forms of the two variable data, for the most part, you're either going to say linear or nonlinear. Does it generally look like it follows a line or it doesn't follow a line? And in this case, I would say that it looks fairly linear. So we're going to record our answer for the form as linear. And then we have to give some sort of explanation. And this is just sort of a general explanation, but we're going to say that the points generally follow a straight line. Now, there is a chance that you might get a data set that has a little bit of a curve to it, in which case you would say that the form is nonlinear. All right, let's move on to question number 4, which says, what is the strength of the relationship? So here's the deal with this one. Once you have decided your form, and for us that was linear, the strength is an indication of how closely do all of those points fit with the form that you have selected. Now, because we've selected the linear form, we want to know how closely do all of these dots fit that particular line. While there are some that are above the line and some that are below, they are generally fairly close to that line of best fit. So I'm going to say that the strength is fairly strong. Now, there is not a specific rule for deciding whether it's weak or moderate or strong or fairly strong. You sort of have to go by feel. I wouldn't call this one a very strong, but I think fairly, using an ly word there, is pretty safe. So we're going to call that a fairly strong relationship. And to explain why, we're going to say that the data points fall fairly close to the line. Okay, now we're going to take a little bit of a pause here before we summarize, and that's to notice exactly what we have commented on in the first 4 questions here, because each one of these questions is giving us something that's really important. In question number 1, where we indicated positive or negative, what we were describing there is the direction of the relationship. And generally, your direction is either going to be positive or negative. In number 2, we were trying to identify unusual features. In number 3, we were trying to define the form of the relationship. And in number 4, we were talking about the strength of the relationship. So listen, these are the 4 things that you want to make sure that you address when you see a question that says describe the relationship between 2 variables. Okay, this might look sort of similar to what we talked about on Monday. For one variable data, we had SOCs, right? Shape, outlier, center, spread. Well, here we're going to use a different acronym. It is D-U-F-S, Duffs. That reminds you of the 4 things that you want to make sure you comment on. And just like we did with one variable data, we need to make sure that we include context of the problem. All right, that's just a general rule on the AP exam. So Duffs plus context is the way that we're going to remember what to talk about when we're describing the relationship. So in the summary here, what I'm going to attempt to do is to take all 4 of those ideas and put them into one nice, neat sentence. Okay, so here we go. Here's my best attempt. Describe the relationship between GPA and SAT. There is a fairly strong positive linear relationship between GPA and SAT with one outlier at a GPA of 3.4. There's my nice, neat, concise sentence. Now let's make sure that it has everything that we need there. All right, let's go in order of Duffs. D is direction. Yes, I see direction. My direction is positive. U, unusual features. Well, that's down here. I've talked about the outlier. F is form. The form here is linear. We've taken care of that. And then S is strength. We've used the word fairly strong to indicate our strength. And then context, well, that's actually right here, GPA and SAT. I've clearly indicated the two quantitative variables that we're describing the relationship between. So what I like about this sentence is it takes care of all four of those things in one nice, neat sentence. Describe the relationship. Okay, let's go ahead and move on to number 5. Now for number 5, the equation of the least squares regression line, we need the numbers from the computer output, and really these are the two numbers that we need, the y-intercept and the slope. And so let's just copy those down here. We've got y hat equals our a value 724.4 plus our b value 169.0 times x. But here's the deal. I'd like to do a little better than that with our equation for the LSRL. I'd like to know what x and y represent in this particular context. So we're actually going to use contextual variables here. So we know that y, the thing we're trying to predict, is the SAT score. So I'm going to rewrite this as SAT, and I'm going to include the hat on it, which means predicted SAT, because we're trying to predict the SAT from the GPA, equals 724.4 plus 169.0. And now instead of x, I'm going to put in my x variable here, which is GPA. And now I have a very clear understanding of what we're using that line for, which is to predict SAT scores. Okay, number 6 is to interpret the slope of the LSRL. Well, we've got our slope right here, 169.0. We've talked a little bit about this already. And I guess the little trick that I'm going to give you is to think of it as being the change in y over the change in x, which for this particular context is going to be the change in predicted SAT over the change in GPA. And then to think of that number as actually being a fraction over 1. So 169.0 over 1. And we did this in the homework problem already now. We just need to turn this into words. So the change in GPA of 1 corresponds to a change in predicted SAT of 169. Here's what it would look like in words. I would say this. For every increase of 1 in GPA, the predicted SAT score increases by 169.0 points. Let me highlight a couple important parts of the way that we've worded this here. All right, we're talking about an increase of 1 in x, which in this case is GPA, but we've included context. Very important here that you say predicted or estimated SAT score. And then look, we've used this word increases. And the reason why it increases is because this 169.0 is a positive value. If that had been a negative value, then we would say decreases. And then we've also tried to include our proper units here. So that looks like a pretty darn good interpretation of the slope. Now, a quick side note here. It says for an increase of 1 in GPA, the SAT would estimated to go up by 169. Now, does that mean that if I took one of my students and I logged into the computer and I changed their GPA by increasing it by 1, would that cause them to do better on the SAT? Well, hopefully you said no here. We have a correlation here, but we don't have a causation. And that's because we didn't set up an experiment here. This is just observational study data. So that's the classic example of correlation does not necessarily imply causation. All right, now let's get to that y-intercept. So the y-intercept we know is the 724.4. And if you think back to your algebra days, the y-intercept was when the x value is equal to 0. And in this case, the x value would be the GPA. So I don't know that this makes a whole lot of sense, but we're going to write it out anyways. It says, for a student with a GPA of 0, the predicted SAT score is whatever the y-intercept is, 724.4. So while that doesn't necessarily make a whole lot of sense, I suppose it's possible there could be a student with a GPA of 0.00. but you do need to know how to interpret the Y-intercept in the context of a problem. All right, I think we are ready to move on to page 2 of the activity. So if you can flip to the next page here. Still the same context, still the same scatter plot, same computer output, but there is something that's new here, and that is this graph right here, which is known as a residual plot. So we need to do some thinking about what this residual plot is showing us and what things we can get out of that particular residual plot. So let's just dig into the questions here. All right, question number 8 says predict the SAT score for a student who has a GPA of 3.4. Well, this is the whole point of finding a line of best fit, so we can make a prediction. So let's go ahead and see if we can predict the SAT score. And we have our equation here, right? We know our A value and we know our B value. So it is 724.4 plus 169.0 times the GPA. And this particular student has a GPA of 3.4. And that is telling us we have a predicted value of 1299. Now, let me make a connection here to what you see in the scatter plot and the line of best fit. What we're trying to do here is to make a prediction for a student with a 3.4 GPA. So what we're really doing when we plug 3.4 into the line of best fit is we're going up to the line of best fit here, and we're looking for the Y value that goes with that particular X value. And if you follow that all the way over, it seems reasonable that 1299 would be that Y value right there. So we're actually just confirming something that we see in the graph there from the line of best fit. All right, let's move to question number 9, which says the student with a GPA of 3.4 got an actual SAT score of 1113. Calculate and interpret the residual. Okay, we first of all need to know the formula for the residual, right? I referenced it on the previous page, which is that it's how far away that point is from the line. And the way we calculate that, or the way I like to write it, is actual Y value minus the predicted Y value, right? And students often want to mix those up, but listen, it's very easy if you look at the order of those. AP, right? You're sitting in an AP statistics class. That should come natural to you. At actual value minus the predicted value. So for us, the actual SAT score for this student was 1113. The predicted SAT score, well, we said we thought it was going to be 1299. And so that means that we're going to get a residual of negative 186. Now let's see if that makes sense in the picture here. All right. In the picture, look, here's the student that actually has the 3.4 GPA. And sure enough, if you follow that over to the Y-axis, it seems reasonable that that student's actual score was 1113, right? And what we're finding now is the difference between the predicted value and the actual value. And what we're getting is the residual. And so we're saying that this residual is equal to negative 186. And why is it negative? Well, that's because the actual value was less than the predicted value. And you can see that because that dot is lower than the line of best fit. So when we interpret the residual, we need to make note of that. So here's how we're going to interpret this. We're going to say the actual SAT score for the student with a 3.4 GPA is 186 points lower than predicted by the LSRL. And you'll notice here, very important is that I'm using this word lower. That explains why we have a negative value for our residual, because the actual value is less than the predicted. And so sure enough, if you look at the scatter plot, any of these values that are below the line of best fit, those are all going to have negative residuals. And all these values above the line of best fit, well, those are going to have positive residuals. All right, let's move to, oh, by the way, I want to note here, when you look at the residual plot, find the X value, the GPA of 3.4, and you can find that student that we've just did the calculation for. And sure enough, if you look over here at the residual, it seems reasonable that that residual would be negative 186, right? You can see that in the residual plot. So let's talk a little bit more about that residual plot. Question number 10 says, what does the residual plot indicate about the use of a linear model for the data? Okay, a couple of things that I'd like you to notice in the residual plot. First of all, this value right here is always going to be 0. That's going to be at the center of the residual plot. And you're going to have some values above it and some below. Just like we said in the scatter plot over here, some of the points are above the line of best fit, which means they have a positive residual. Some are below the line of best fit, which means they have a negative residual. And the line of best fit will position itself so that if you were to add up all of those residuals, the sum of those residuals is always going to be equal to 0. Which seems reasonable when you look at the residual plot, right? Some above, some below. If you were to take them all and add them up, you'd get 0. In fact, you'd get an average of 0 as well, right? That the average residual is 0 because adding them all up gives you 0. And then the other thing I guess I want to make sure to make note of is that on the x-axis, we are plotting the x variable, which is most common with the residual plot. And then on the y-axis, we are plotting the residual, which is what makes it a residual plot. Now, what is this residual plot telling us? Well, when you look at the residual plot, there's not really any pattern that's emerging out of that, right? We don't see a clear curved pattern in the residual plot. And honestly, this is a good thing. That means that in the scatter plot, we have sort of an equal scatter above and below the line of best fit, which is good. That means that the line is a good model for the data. So here's what we're going to say for this. We're going to say because the residual plot does not show a clear pattern, which is a good thing, does not show a clear pattern, that means that the linear model is appropriate for the data. So what would happen if we did have a pattern that was left over in the residual plot? I'm just going to put a little note here off to the side. These are what I call red flags. If you were to see a residual plot that looked like one of these, that's a red flag to you that the model you've chosen might not be the best model. So here's the first example, residual plot, right? So 0's there. If you had a very clear, what I call smiley face pattern, right? You see the smiley face there? That is an indication to you that whatever model you chose that created that residual plot is not a good model for the data. Similarly, another red flag is the frown face. So listen, if you have smiley face or frown face in your residual plot, that is not a good sign to you. That is telling you that the model you've chosen is not necessarily a good model. Now for us, we've got an equal scatter above and below. The 0 line there, that seems to indicate that the linear model is a decent model for this set of data. Okay, so let's move on to question number 11 and 12, which is straight up interpretations that you just have to know. Got to know a couple of interpretations here. The first one is for what's called the standard deviation of the residuals, S. Well, it's not likely you'd have to calculate that, but it's more likely you'd have to interpret it. So if you look up here, we know the value is 116.9. All right, you can get that right from the computer output, but we need to understand what that represents. Okay, it's the standard deviation of the residuals. But remember, the residuals have a mean of 0. So when we think about standard deviation, we normally think of it as being the typical distance away from the mean. Well, if the mean is 0 and it's the typical distance away from 0, it's sort of telling you what a typical residual looks like. And if we think of the residual as being the error in our prediction, what we have here is what's called the typical prediction error, right? That's what S represents. So sometimes I'll even call it that. I will call it the typical prediction error. It's telling you what your typical residual might look like. And you probably want this value to be as small as possible. Now, in terms of interpreting it here, we want to talk about prediction error and sort of like what a typical prediction error looks like. So here's how I'm going to word it. I'm going to say the actual SAT score is typically about 116.9 points away from the score predicted by the LSRL with X equal to GPA, right? The actual SAT score is going to be about 116.9 away from the score predicted by the LSRL. I'm just going back to this definition of residual, right? Actual minus predicted, and we have the typical residual here, okay? So 116.9 points, that's kind of far off if we're trying to predict somebody's SAT score, right? So we would like that value to be as small as possible, right? The smaller that value is, the better our model is at predicting. Okay, let's move to question number 12, which is to interpret the coefficient of determination. All right, well, we're going to steal that value right from the computer output. Make sure you're grabbing R squared, not R squared adjusted. It is 77.8%. And just as it says right here, it is in fact the R value and then squaring it. So the R value, which is the correlation, if you were to just take that and square it, would give you 0.778 or 77.8. Now, in terms of interpreting it, you sort of have to know this one. There's a little bit of like a sentence frame that you're going to want to use here. And we're trying to describe that percentage. So I'm going to say 77.8% of the variability in the Y values. And in this case, that's SAT scores. So I'm going to say of SAT scores is accounted for by the LSRL with X equal to GPA. That's just typical wording that you'll see even on the AP exam. Now, the other way that you'll see it every once in a while, instead of saying accounted for, they'll say explained by the LSRL. So I'm going to put that in there just as a quick reminder. But this is one of the ones that you sort of need to know the fill in the blank exercise of interpreting the R squared coefficient of determination. All right, we've got one final question here. Number 13 says, do the data provide convincing evidence of a positive linear relationship between GPA and SAT for all seniors at this high school? Okay, we only have a sample of 10 students here, right? But based on our sample, do we have some evidence that there's a positive linear relationship? Well, sure enough, if you look at the slope value, right, our slope value was 169.0, which is very clearly a positive linear relationship, right? It's greater than 0. So we do have some evidence based on this sample of 10. But the question is not asking about the sample of 10, it's asking about all seniors at this high school. So this is where we would have to make an inference about the population from our sample. And we have to remember that every time you take a random sample, you're going to get different results. So if I were to select a different random sample of 10 seniors, I wouldn't get the same scatter plot. I wouldn't get the same line of best fit, and I wouldn't get the same slope value, right? So that value is going to vary because of sampling, right? Sampling variability. So the question is this slope value a strong enough slope value that we can say that there's convincing evidence of a positive linear relationship for all seniors? Well, of course, we need inference to answer this, which means a significance test. And specifically, the significance test that we would need here is what's called a t-test for slope. So we'd have to actually carry out the test and find a p-value and make some sort of conclusion after we did the significance test. So there is another video that you can watch that has the explanation of how to do a t-test for a slope. But I do want to put the quick reminder out that for the 2020 AP Statistics exam, the t-test for slope will not be covered on the 2020 AP Statistics exam. Okay, I think we got through what we needed to. We do need to try and summarize, hopefully, what we've taken away from today's lesson. So let's go to the last part of the activity here, which is to summarize the important ideas. And I'm going to break this down according to the learning targets that I presented at the beginning of the lesson. There were 3 of them. Learning target number 1 was for us to be able to describe the relationship between two quantitative variables. And we learned that there are 4 big ideas that we want to make sure that we address. And the acronym to remember that is Duff's. And let's make sure we know what each one represents. D is direction. U is unusual features. F is form. And S is strength. And let's just put some quick notes about what you could say for each one of those. For direction, this one's pretty straightforward. You're either going to have a positive or negative direction there. Unusual features, we actually mentioned a few of them. We had outliers, which don't follow the general trend of the data and do have a large residual. We have high leverage points, which are going to be points way down on the x-axis or way up on the x-axis. And then we have influential points, which are ones that if you were to remove them would make big changes on the slope, the y-intercept, or the correlation value r. All right, in terms of form, you sort of have 2 choices here in AP statistics, and that's linear or nonlinear. Now, if you take another statistics course in college, you'll get into those nonlinear relationships in a little bit more detail. And then finally, strength. We have different words to describe the strength, ranging from weak all the way up to strong. One thing that you can look at in order to try and determine strength is you can look at R, the correlation value, but make sure you're also taking a look at your scatter plot as well as your residual plot, not just the R value. And then the final thing I want to just make note of here is that you're going to want to address Duff's, but you got to always include context. All right, that takes care of learning target number 1. Learning target number 2 had to do with residuals and residual plots. So let's first just put a little reminder here of the definition of a residual, which is the actual y value minus the predicted y value. And sometimes you'll see that written as actual y value y minus predicted y value of y hat. And then the other thing we looked at in this learning target was what a residual plot looks like. And so a couple of important things with the residual plot. 0 is here. The residual is the thing that's being graphed on the y-axis. Most often you have your x variable on the x-axis. And you know what we would like to see in a residual plot is no pattern, right? If we had something like that, that would indicate to us that the form that we have chosen or the model that we have chosen is in fact a good model for the data. What we don't want to see are the red flag ones we mentioned on the other page. Okay, got one last learning target, and this is all of the interpretations. And I'm not going to write out the entire interpretation because you can look back in the activity. I'm going to give you just the sort of what I call the quick notes. Okay, so if you are asked to interpret the slope, the quick notes is to remember that that is the change in y hat over the change in x, and to write your slope b as a fraction over 1. And then you can say for an increase of x in 1, we predict an increase or a decrease in y of b. All right, for the y-intercept, thinking back to your algebra days, that is the y value when the x value is 0. So I'm going to say that it's the predicted y value when x equals 0. But you would, of course, have to put that in the context of the problem. All right, the next one is S, which is the standard deviation of the residuals. And remember, I called that the typical prediction error. Right, it's what your typical residual is, or typically how far is the actual y value away from the predicted y value. And then finally, the last one that we talked about is interpreting R squared, which is the percent of the variability of y, although you'd use the context of whatever that variable is, explained by the LSRL with x equal to, and you would indicate whatever the explanatory variable was there. All right, so the next thing that you'll see on here is your homework problem, one simple multiple choice problem that I've taken from AP Classroom that I'd like you to try before you check in with Mr. Murphy tomorrow. I sure hope that today's lesson was valuable for you and a good reminder of some things that you learned earlier in the year. If it was helpful to you, please give me a thumbs up there in YouTube. I would appreciate that a lot. And I certainly hope that you will be back here tomorrow with Mr. Murphy. And then I will be back on Friday where we will do FRQ Friday. See you then.